Good evening, everyone. So, in the last lecture, we discussed about the motion under gravity. We discussed about the equations of motion when the body moves under gravity, right? When the body falls under gravity, or when the body is projected particularly upwards under gravity, right? Now, in this lecture, we'll be starting with the numerical problems of the topics that we discussed in the last two lectures, and then we'll be starting with the graphical analysis of motion under gravity or motion along a straight line, right? So here we have first question in front of us on the screen. The question is a ball is released from a height h and it reaches the ground in 3 seconds, right? A ball is released from a height and it reaches the ground in 3 seconds. If the acceleration due to gravity is taken to be 9.8 meter per second square, find the height from the ball was released, right? So we have to find the height from which the ball was released, right? So it's taking time t equal to 3 seconds. So we can use for part A, we know that for part A, we know that we can use this equation v is equal to u plus at, right? And here A is nothing, that's equal to g, that's equal to minus 9.8 meter per second square, right? So initially here the ball was released, or we can say the initial velocity was equal to 0. So our v will be equal to at, right? V will be equal to at, correct? So the time taken by this ball to strike the ground is given as 3 seconds, right? Time taken by this ball to strike the ground is given as 3 seconds, correct? So what we have to calculate the height from where the ball was released, right? Let's suppose this is the ground here, right? Let's suppose this is the ground here, and this is the height h from which this ball was released, right? And this ball was released with speed u equal to 0, and this ball strikes here, right? With some speed v, right? The time taken by this ball is equal to 3 seconds. So the displacement of this ball is nothing, it's equal to height of this tower, right? So h is equal to, that's ut plus half at square, right? And we know that this u is equal to 0, so this will go to 0. So h will be nothing, that's half into a. A is given as 9.8, so it will be 9.8 into t square. T square is 3 square, that's 9 into 9.8 upon 2, right? So it will be approximately equal to 44 meters, right? It will be equal to 44 meters, right? So height of this tower comes out to be 44 meters. The velocity with which the ball will strike the ground. We have to calculate the velocity with which this ball is going to strike the ground. So that's part B. We can use this equation v is equal to u plus at, right? And the initial velocity is given as 0. A is equal to minus 9.8, right? 9.8 meter per second square. And finally, the direction of velocity is also along the negative direction. So we can actually write it as v in the negative direction, right? So we can write v as minus 9.8, and the time taken by this ball to strike the ground, that's 3. So that will be equal to 27. 3 into 8 is 24. So it will be 29.4, right? 29.4 meter per second. So this is the velocity with which this ball will strike this ground. It will be actually minus. Minus sign signifies that the direction of this velocity is along the negative y direction, right? So the speed of this particle when it strikes the ground is 29.4 meter per second, right? Let's move on to the part C. Part C, at time t equal to 2 second velocity and height from the surface. We have to calculate after time t equal to 2 seconds. What is the velocity and height of the ball after 2 seconds, right? So after 2 seconds, the velocity of the ball will be nothing. It will be equal to v is equal to u plus at, right? So it will be equal to 9.8 into t. So it is 19.6, right? 19.6 meter per second, right? And height will be equal to height from the surface, right? Height from the surface. So the distance traveled by this particle the distance traveled by this particle during time t equal to 2 seconds will be, that will be s is equal to ut plus half at square, right? U is equal to 0 here, so this term will vanish. We'll be left with half 9.8 into t square, that's 4, right? So this will be once again 19.6 meters, right? Correct? 19.6. But height from the, this will be the 19.6 from the top of this tower, right? This is the tower like. So the height of this tower is h, and it covers a distance of 19.6 meters in time t equal to 2 seconds, right? The distance from the surface will be h minus this 19.6. So the distance s will be, or height h from the surface will be equal to, that's 44 minus 19.6. 44 minus 19.6 meter. So it will come out to be 24.4 meters, right? So this will be the height from the surface of this ground, right? Let's move on to the question number second. We have question number second here. So the question number second here is, a particle is dropped from height 100 meter, and another particle is projected vertically up with velocity 50 meter per second, right? A particle is dropped from height 100 meter and another particle is projected vertically up with velocity 50 meter per second from the ground along the same line. Find out the height where two particles will meet, right? We have to find the height the two particles will collide or meet. So the situation is like this. Let's suppose this is our ground, right? Let's suppose this is our ground. And this is the height h, that's equal to 100 meter. And from this height, we have two balls. One from the top, it's dropped, right? Another ball is thrown from the bottom, right? It's thrown from the bottom with initial speed as 50 meter per second, right? And this ball is just dropped. We can say that its initial speed is equal to 0 meter per second, right? And after some time, these two balls are going to collide each other, right? These two balls are going to collide each other. Let's suppose that at some point P, these two balls collide each other. And when these two balls collide each other at this point P, right? At this point P, let's suppose after time T, they collide with each other. Okay. So after time T, they collide with each other. This ball is coming down from height h, right? From height 100 meters. And let's suppose the displacement of this ball is S1 and the displacement of this second ball is S2, right? We know that when they collide each other, this S1 plus S2 has to be equal to 100 meters, right? Because the total height is 100 meters. So if the first ball comes S1 meters downwards and the second ball covers a distance of S2 in the per direction, the total S1 plus S2 has to be equal to 100 meters, right? And let's suppose after time t, they collide with each other. So we can calculate this S1 as S1 will be equal to ut plus half gt square, right? So this will be equal to u is 0 for first ball. So it will be half gt square, right? That's equal to S1. And similarly, S2 will be equal to ut, that's ut minus half gt square, right? Ut minus half gt square, correct? So this will be ut minus half gt square, correct? So S1 plus S2 has to be equal to 100, right? That has to be equal to 100. So it means that from here, we can clearly see that S1 is half gt square and S2 is ut minus half gt square, right? So that will be equal to 100. So this and this will get cancelled, right? We'll be left with ut, that's equal to 100, right? And we have to calculate this time t, right? We have to calculate this time t where they will collide, right? The time after which they are going to collide is 100 upon u. and u is the initial speed with which this particle is actually use this speed with which actually particle is being projected, right? Use the speed with which actually this particle is being projected. So 100 upon 50, that's equal to 2 seconds, right? So 100 upon 50 is equal to 2 seconds. So the time t is equal to 2 seconds. This is the time after which these two particles are going to collide each other, right? So they are going to collide each other after, right? So let's do one thing. We have to calculate the position where they will collide. So S1 will be equal to, or S2 will be equal to ut minus half g to square, right? U is equal to 50. So t comes out to be 2 seconds. So 15 to 2 minus, let's suppose value of g is 10. 10 upon 2, that's t square. T square is 4. This this one will get cancelled. So we'll be left with 100 minus 20, right? So it will be equal to 80 meters. So at a height of 80 meters, these two balls are going to collide. At the height of 80 meters, these two balls are going to collide each other. So here I have taken the value of g equal to 10 meter per second square, right? This is how we'll be calculating the height at which the two balls are going to collide, and we also calculated the time after which the two balls will be colliding, right? So let's move on to the question number 3 here. Question number 3 here is a particle is dropped under gravity from rest from a height h, that's and it travels a distance 9h over 25 in the last second. The height h is. So let's to ease our calculation, let's take this value of g equal to 10 meter per second square, right? Instead of 9.8, we are using the value of g here equal to 10 meter per second square, right? To ease our calculations. A particle is dropped under gravity from a rest from a height h, and it travels a distance 9h over 25 in the last second. So it means that, let's suppose this is the height h from which this particle is dropped. This is the height h from which this particle is dropped. And from this height as the particle is dropped, it means the initial speed of this particle is going to be 0, right? And after time t, that let's suppose that time t is equal to n. This is the after time t that's equal to n. This is the time of flight, right? This is the time of flight. It means this is the time taken by this particle to strike the ground, right? So after time t equal to n is the time of flight, or we can say t is equal to n is also the last second, right? T is equal to n is also the last second, right? So this is the last second. We can say two things. Time of flight, either time of flight is the time taken by this particle to strike the ground, or we can say that this is the last second of the time of flight. Suppose that if the time of flight is 9 seconds, so last second will be ninth, right? If time of flight is 20 seconds, then the last second will be 20th, right? So that's how we can also interpret it in this way, right? And it travels a distance. Uh, a particle is dropped under gravity from a height h, and it travels a distance 9h over 25 in the last second. The height h is. The distance it travels in the last second is that's 9h over 25, right? And we know that distance covered in the nth second, that's given as u plus a by 2, right, into 2n minus 1. So this is the distance covered in the nth second. And here we have to calculate the distance covered in the last second, right? So n here will be the last second. So u is equal to 0 initially because it is dropped, right? So Sn will be equal to g by 2 into 2n minus 1, because the acceleration here is the acceleration due to gravity. And in the last second, the distance traveled, that's 9h over 25, right? 9h over 25. We have to calculate this height, right? We have to calculate this height. Now we know this time of flight is also that's equal to under root of 2h over g, right? 2h over g, 2h over g, right? So we can write n is equal to under root of 2h over 10, right? Or it will be equal to root h over 5, root h over 5. So from here, our g by 2, right, will be left with 2 times n. So n here is root h over 10 minus 1, right? So we have to calculate this height h. So from here, the height h will be, so 2 into 9 will be 18h upon value of g is 5, right? So it will be upon 50, correct? So it will be 2 under root of h over 10, right? Minus 1. So from here we can rewrite it as 18h upon 50 plus 1. That's equal to twice root h over 10, right? That's twice root h over 10. So from here we can do one thing. We can just try to solve it in this way. Let's suppose if we can do one thing, we can square it on both sides, like 8h upon 50 plus 1 whole square, right? And it will be left with 4h over 10, right? That will be equal to 2h over 5. So from this equation, we can easily calculate the height h, from which this particle was dropped, right? So here t is equal to nth second or the time of flight, that's equal to under root of 2h over g. So our n is equal to 2h over g. We have taken the value of g here equal to 10 meter per second square. We can substitute the values or rearrange this equation to calculate the height h, right? So that's it. We'll be moving forward to the question number 4, right? This is our question number 4. The question number 4 says that a ball is thrown upwards from the top of a tower, right? The height of the tower is given here 40 meters high with a velocity of 10 meter per second. Find the time when it strikes the ground back, right? So here you can see in this diagram, a ball has been fired vertically upwards or thrown vertically upwards with speed 10 meter per second. And after some time, the ball strikes back to the ground, right? And we have to calculate this time when this ball is going to strike back from the height of this tower, 40 meters, right? So let's suppose if we take this surface as origin, right? If we take this height as origin or reference, right? If this is taken as reference, right? Then all the direction in the upward direction will be taken as positive and rest of the direction in the downward direction will be taken as negative, right? So it means that the initial position of this ball, the initial position xi with respect to the reference, that is equal to 0, and the final position with respect to the reference, that's equal to minus 40, right? That is equal to minus 40, right? So if we calculate the displacement s, that is final position vector minus initial position vector, so it will be nothing. It will be equal to minus 40. So the displacement of this ball is equal to minus 40, right? That's equal to minus 40. And g, the value of g here is that's equal to minus 10 meter per second square, right? And the velocity, initial velocity here is positive. It will be taken as plus 10 meter per second, right? So the equation we will be using here is, we'll be using displacement equation, that s is equal to ut plus half at square, right? This will be the equation we'll be using here. S is equal to ut plus half at square. Here the displacement comes out to be minus 40. That's minus 40. And u is 10 t. And a is minus 10, that's minus 10 by 2 t square, right? That's 10t minus 5t square, right? That's equal to minus 40, right? Or we can rewrite it as it's minus 5t square. We can rewrite it as that's minus 5t square plus 10t, that's equal to minus 40. So here we can cancel this 5 and here will be 2, right? This is 5 is a 40, right? We can rewrite it as t square minus 2t, that's equal to what, 8, right? That's equal to 8. Or we can say that it's t square minus 2t minus 8, that's equal to 0, right? That's equal to 0. So we can rewrite it as, we can solve this quadratic equation, that's t square minus 2t minus 8, that's equal to 0. We can solve this quadratic equation like, so we can split this here, minus 4t plus 2t, right? That's minus 8, right? That's equal to 0, right? We can take t here common, right? If we take t here common, so we'll be left with t minus 4. And if we take 2 here common, we'll be left with t minus 4, right? That's equal to 0. So it means that t minus 4 and t plus 2 will be the two factors of this equation, right? Or we can say that t is equal to 4 comma minus 2. So we'll be taking only the positive time here. So it means that after time t equal to 4 seconds, right? After time t equal to 4 seconds, this particle is going to strike back this surface, right? So after time t equal to 4 seconds, after 4 seconds, this particle is going to strike back. This particle is going to strike back this ground after time t equal to 4 seconds, right? So it will take 4 seconds for this particle to strike back the ground, right? So that was it with respect to this question, right? Now, moving forward, we'll be discussing some of the important aspects of the motion under straight line or motion along a straight line. That's the graphical analysis of a motion, right? We'll be studying different graphs and try to interpret different graphs, right? So let's start with graphical analysis, or we can say graphs of a motion under straight line, right? Right? We'll be studying all these graphs one by one. So let's start with position time graph, right? We'll be starting with the position time graph. So let's suppose this is our Cartesian system, right? This is our Cartesian system. This is our time axis and this is our position axis, right? So x here represents the position of a particle and t on the x-axis represents the time, right? So let's suppose the particle moves like this. This curve represents the position of the particle at different times, right? This curve represents the position of a particle at different times. If we calculate the slope of this particle, right? If we calculate, suppose this is the point A, this is the point B, this is the point C. We know that tangent to the curve is represented by the tangent to the curve at some point has some slope, and the slope of that tangent is calculated using the derivative at that point, right? So suppose that if we take a derivative at this point for this tangent at A, let's suppose this is the tangent at A and this is the tangent at B, right? And this is the tangent at C, right? So these are the three tangents, tangent at A, tangent at B, and tangent at C. So the tangent or the derivative of this position time graph, that's dx over dt, dx over dt, this represents the velocity, right? And we know that derivative is nothing, is the slope of, it represents slope, or we can say slope of position time graph, position time graph, slope of position time graph gives velocity, right? So the slope of position time graph is nothing, it gives us the velocity, right? It gives us this velocity. We can see at point A, the slope is positive, and at point B also, the slope is positive, and at point C, the slope is once again positive, right? But we can also see that slope at point C is greater. Let's suppose the speed at point C is Vc and speed at point B is Vb, or the velocity at C is Vc, velocity at B is Vb, and the velocity at point A is Va, right? And we know that the slope, greater the slope of position time graph at a point, greater will be the velocity at that point, or greater will be the magnitude or speed of particle at that point, right? So we can see clearly here that the slope at point C is greater than point B than point A, right? We can say that speed at C is greater than speed at uh, A, right? Slope at A is greater than the slope at B. So we can say that speed at C is greater than speed at A. That's greater than speed at point B, right? So from this, we conclude that the position time graph gives us the slope of a position time graph gives us the velocity, right? If the slope is negative, it means the velocity is negative. It means by negative velocity, we mean that the particle is directed along the negative direction, right? We're taking this direction as the positive, right? And the opposite direction as the negative, right? This direction is taken as negative, right? And the time axis is always taken along the positive x-axis, because we do not talk about the negative times, right? So here the slope of a position time graph gives the velocity at some point, right? So in this case, the slope at C was greater than A than B, right? So VC is greater than VA, greater than VB, right? Let's move on to the next point. Let's suppose we have a position time graph like this. This is our position time graph, right? And let's suppose this is how the position time graph varies with time. So this is our position time graph, right? This is position versus time graph, right? We can see at different times, let's suppose this is the point C here, this is the point P here, and this is the point A here, right? Point A. If I draw a tangent here, this is the tangent here, correct? And at this point B, this will be the tangent, and this is the point C here, and this will be the tangent at point C, right? This is the tangent at point C. So the tangent at point C is nothing, it's parallel to x-axis, right? It's parallel to x-axis. Or we can say the slope here is 0, right? Slope is equal to 0. Slope is 0. Or we can say tx over tt, that's the velocity, that's equal to v, that's equal to 0. It means the point where the slope of a position time graph is equal to 0. It means the particle is at rest at that point. The velocity of that particle is going to be 0. So we can clearly interpret from this graph that as we move from origin, as we move from time t equal to 0 to some time t naught, right? You can see that the slope is continuously decreasing. If the slope is decreasing, it means the speed of this particle is continuously decreasing, right? If the speed is decreasing, then at some point the speed becomes 0, or the particle stops, or the velocity of the particle is 0. So from here we can say that slope at A is greater than slope at B, that's greater than slope at C, right? Which is equal to 0, right? Which is equal to 0, right? So here in this graph, the speed of this particle is actually decreasing with time and eventually becomes 0 at point C, because the slope at point C is equal to 0, right? And let's discuss case third. So this is again our position time graph, right? Let's suppose this is the position time graph, right? This is the position time graph at different times, right? This is the position time graph at different times. Let me call here, these are the 2 points. This is the point A here, and this is the point B. If I draw a tangent at point A, so it will be like this. This is the tangent at point A, and this will be the tangent at point B, right? We can clearly see that slope at point B, slope at B is more then slope at A, then slope at A. If the slope at B is more than slope at A, it means the velocity is greater than, or the speed is greater than at point B than point A, right? Or we can say that here the speed is increasing continuously, right? The speed is increasing, the speed is not constant, the speed is changing because the slope of position time graph is changing. We can say that this is an accelerated motion, right? This is an accelerated motion because the speed is changing at different points, the speed is different. This is an accelerated motion, this is also accelerated motion, right? But speed here is decreasing, or we can say it's a retarded motion, right? It's a retarded motion. And here in this case, it has both increasing speed in this portion and decreasing speed in this portion. So it has both positive accelerations as well as the negative accelerations, right? So here in this case, the speed at point B is greater than the speed at point A, right? So the velocity at point B is greater than the velocity at point A, or we can say it's an accelerated motion, right? It's non-uniform. It's a non-uniform motion, right? Velocity is not constant. It's a non-uniform velocity, right? Let's discuss the final case. That's the case 4 with respect to the position time graph. So here we can say that let's suppose this is our position X, this is our time axis, right? And let's suppose this is the position time graph, right? This is the position time graph. This is the XT graph. And we can see that for this line, the slope at every point is same, right? The slope at every point on this straight line, it's a straight line. We know straight line is represented by y is equal to mx plus c, where m is nothing, is the slope, right? M is nothing, it's called slope, and it's a constant for a straight line, right? It's a constant for a straight line, right? Slope is constant for a straight line. So for point A and for point B or for point C, the slope is same, right? Or we can say that the speed at C is equal to speed at B, then speed at equal that speed at point B, right? So it means that when the position time graph is a straight line, the speed is constant, or we can say the velocity is a constant. Velocity is not changing. When the velocity is not changing, we can say acceleration is zero, right? Acceleration is zero, right? Or we can say velocity is constant, right? Velocity is constant. And let's suppose this is the angle theta here, right? And we know that the dy by dx is nothing, is the slope of a curve at some point, right? It is also equal to tangent, right? That's tan of theta, right? That's tan of theta. So if we have to calculate the speed of this particle at some point A, B, or C, it's a constant slope. We can calculate speed as that's v is equal to tan of theta here, right? So this is the speed. This is how we can also calculate the speed, right? Here. So also we can calculate the speed using the drawing the tangent at some point on a curve and find out the angle with angle which the tangent makes with the positive x-axis, and the tangent of that angle will give us the velocity at that point, right? So this was with respect to the position time graph, right? Let's move on to the next topic. Let's move on to the next part. That's the velocity time graph, right? Velocity time graph. Let's discuss velocity time graph. Let's suppose this represents a velocity time graph, right? Here once again, we can, this is the velocity time graph, right? This is the velocity time graph, right? We can also say that, let's suppose this is the angle theta here, and we know that it's a straight line once again. So the slope of this velocity time graph is a constant, right? Slope is constant. Slope is constant. And we know the slope of the curve at some point is nothing, it's dv over dt here in this case. And dv over dt is nothing, it represents the acceleration, right? It's the acceleration. That is equal to a, right? So here the slope of velocity time graph represents acceleration, right? Slope of velocity time graph gives the acceleration, right? If the slope is positive, the acceleration is positive. If the slope is negative, the acceleration is negative, right? So this is, or we can say in this case, dv over dt is nothing. That's equal to a here, or that is equal to tan of theta, right? That's equal to tan of theta, right? That's equal to tan of theta. So the slope of velocity time graph gives us the acceleration, right? If the acceleration is positive or the slope is positive, the acceleration is positive, right? If the slope is negative, then acceleration is negative, right? So we know that we can also rewrite it as dv over dt, dv over dt, that's equal to a, right? That's equal to a, that's acceleration. And we can shift this dt on the RHS side. And if we integrate it on both sides, let's suppose at time t1 and time t2, right? The velocity was u and the final velocity is u, right? The final velocity is v. So if we integrate it, what we get is v minus u. That's nothing, that's the delta v. That's nothing, that's change in velocity, right? Change in velocity, right? Change in velocity, right? So that's equal to integral of a dt, right? From t1 to t2. And we know that the geometrical interpretation of definite integral is nothing. It represents the area under the curve, right? So the area under the acceleration time graph gives the change in velocity, right? Area under the acceleration time graph gives the change in velocity, right? So it's nothing, it's the area under AT graph, right? AT graph. So area of under acceleration time graph gives the change in velocity, correct? So it gives the change in velocity. Or we can say that dv over dt is equal to a, right? Or we can say that our velocity is nothing, it's dx over dt, right? That's how we define the velocity of a particle, right? That's the rate of change of position vector with respect to time. If we integrate it also, that's integral of v dt, that's equal to dx, right? Let's suppose initial position vector is xi and the final position vector, final position is x final, right? And the initial speed is u and the final speed is v, right? This integral of v dt, this is nothing, it represents area under vt graph, right? Area under vt graph. So that's nothing, that's equal to x final minus x initial. It's nothing, it's equal to displacement, right? That's equal to displacement. That's equal to displacement. Or we can say that area under velocity time graph gives us the displacement, right? So this is a very important point. Area under PT graph, that's the velocity time graph, gives us the displacement, right? So area under VT graph is nothing, it gives us the displacement. And one more important point was area under acceleration time graph gives change in velocity, right? So area under acceleration time graph gives the change in velocity. Or the area under the velocity time graph gives us the displacement, right? Let's suppose this is the velocity time graph. This is the velocity time graph, right? So this is the velocity time graph, right? This is the velocity time graph. You can see here, this is the velocity time graph like this. We can see here at different points like point A and point B. If we draw a tangent at point B, this will be like this. And at point A, the tangent will be like this. You can say that dV or dt, or the slope at point B, right, at B is greater than the slope, that's dV or dt, at point A. Or we can say that acceleration at point B is greater than acceleration at point A. That means that it's a case of non-uniform acceleration. Acceleration here is not constant, acceleration is different, so it's a non-uniform acceleration, right? And velocity is increasing, right? Velocity is increasing. Velocity here is increasing. In this case, the slope is always positive. It means acceleration is always positive. It means that the velocity is increasing continuously. But at different times, the acceleration is different. At point B, the acceleration is greater than at point A, right? It means that particle moves at greater velocity at point B than at point A, right? So it's also that VB is greater than VA, right? So that's it for today. In the next class, we'll be discussing about the speed time graphs and the acceleration time graphs. So till then, take care and goodbye.